Okay, so this next one is the 80th one. Here n is a positive integer greater than 1 and h denotes the set of permutations. I think we will have I forgot to write this, in the symmetric group of degree n in Sn, H is the set of those permutations in Sn that can be expressed as a product of a multiple of 4 transpositions. This is very confusing, this line. In fact, when I first went through it, I did not understand what the author is trying to say. But after thinking for some time, it came to me what the author is trying to say here. Let's just read the line once more. Let H be the set of all permutations in Sn that can be expressed as a product of a multiple of 4 transpositions. At once, it seems meaningless, it sounds meaningless, it looks like something is wrong with this statement, but what the author is trying to say is this, that if you consider any arbitrary element, say tau in H, then tau can be expressed as a product of 4n number of transpositions, where n is some positive integer. That's why you see it is the set of all permutations in Sn that can be expressed as a product of a multiple of 4 transpositions, means a multiple of 4 number of transpositions. That means the number of transpositions involved in that product is a multiple of 4. That's what the author is trying to say. And this is another example which another example of a situation which I don't like is unnecessarily using too many words. If you just simply write that the number of transpositions should be of this form, then it becomes absolutely clear. But anyway, so we understand what he tries to say. So let's now see. What do we have to show? We have to show that this H is actually equal to the alternating group of degree n. Okay. So here is the solution. And just to make things clear, since in this form things are looking confusing, let us start off like this. Note that H consists of all I was going to write transposition, all permutations that can be written as a product of four n transpositions, where n is a positive integer, not any fixed positive integer, of course, depending on the permutation. Okay, so at once we see that because every element of H is a product of that many transpositions, and that many number is an even number. In fact, it's a multiple of 4. So all the transpositions in all the permutations in H, I keep messing up this transposition and permutation, that is, all the elements in H are even permutations. That means they are all in AN. So we write clearly H is a subset of AN. Now we want to prove that the reverse inclusion is also true. Now let sigma be any element in AN. That means sigma is an even permutation in Sn. So sigma is expressible as a product of an even number of transpositions by the definition of an even permutation. So we can further have this, let sigma be this product A to K, B to K for some positive integer K. Okay, so that is just a consequence of sigma being an even permutation. Now we need to prove that this sigma is actually in the set H. Okay. Now two cases arise depending on what type of number 2k is. If 4 divides 2k, that is a possibility. The positive integer 2k may be divisible by 4. If that is the case, then clearly this product itself is a product of a number of transpositions where that number is a multiple of 4, and hence by the definition of H, this sigma, it just belongs to H. So we write if 4 divides 2k, then sigma belongs to H. So now we consider the other possibility. Assume that 4 does not divide 2k. Now we know from the division algorithm that any integer is of one of these 4 forms. That is, either it's of the form 4m or 4m plus 1 or 4m plus 2 or 4m plus 3, where m is some integer. Any integer whatsoever you choose from the set of integers, it will be of exactly one of these 4 forms. And that is because when you say your chosen integer is some n, so when you divide this n by 4, the remainder can either be 0 or 1 or 2 or 3. These are the 4 possibilities, and accordingly the integer n will be one of these 4 forms. Now think of 2k in place of n. Can 2k be of this form? No. Why? Because this is an odd integer, but 2k is even. Similarly, 2k cannot be of this form either, 4m plus 3. Again, because 4m plus 3 is odd, but 2k is even. But now our 2k cannot be of this form also. because we are assuming that 4 does not divide 2k. So that leaves us with only this, that is 2k must be of this form. So we write then 2k is equal to 4m plus 2 for some non-negative integer. Okay, we were going on saying positive integer. Why suddenly non-negative integer here? We want non-negativity here in order to include the case n equal to 2k equal to 2, because to have that we need m to be 0. So if you take m to be positive, then that case 2 will not be covered. Just for that we are considering non-negative integer. Then sigma can also be written like this. Why? That is because this 2 cycle and this 2 cycle, which are the same thing, they will vanish and they will give us the identity permutation. So that is why we will just simply get that same sigma. And note one more thing which one may overlook in this whole solution is that in the exercise, if you go back a little in this video, you will see that in the exercise it is mentioned that n is greater than 1. So that means we at least have 1 and 2, at least 2 symbols are there for us. So that's why we can choose this 2 cycle 1, 2 in Sn. So now what happens to this product? Originally it had how many transpositions? 4m plus 2, but now 2 extra transpositions have been added. Note that we have not been told that the transpositions have to be disjoint permutations, no. Just the number of them matters. They may be non-disjoint also, just like this one here, both are the same. So now the total number of transpositions is 2k plus 2, that is 4m plus 2 plus 2. So which is 4m plus 4, so that is a multiple of 4. Note that in the above product, the number of transpositions is 2k plus 2. Which is equal to 4m plus 2 plus 2, that is equal to 4m plus 4. So by the definition of capital H, sigma belongs to capital H. So we have shown that no matter what the case is, sigma, which was arbitrarily chosen to be an even permutation that is coming from an, now belongs to H. Hence, an is also a subset of H. We have thus proved that H is equal to an, and that was our aim. So here the solution ends. Now after this we have exercises 81 and 82, which are about some arrangements of tires, or it has something to do with rotations of tires in different types of cars, that is front wheel vehicles, rear wheel drive vehicles, something like that. So the solution to the next one, that is the 81st one, is already available at the back of the text. So I want you to go through that solution and try to understand what the author has said there. And based on this, the next one, that is the 82nd one, exercise number 82, its solution is not available, and that is a homework. Based on what you understand from the given solution to 81, you try to then solve 82. See if you can get it. If you don't get it, please let me know. I will then do it for you. So instead, what we are now going to go through those two. They are now left to you. Instead, we look at 83. Let's see, this is the last one in this set of exercises, so let's see what it has to say. What would be wrong? What would be wrong with using the two-cycle notation one comma one instead of the one-cycle notation? To denote or indicate, okay, let me write indicate, let me not change that. To indicate that a cycle sends 1 to 1. So here the question is this. We know that when we consider a cycle which does not change a symbol, then that symbol actually does not appear in the cycle. However, if a permutation does not change 1, say the symbol 1, then we may indicate that fact, we usually indicate that fact by either not mentioning that at all in the symbol for that cycle, or we use this symbol to indicate that the cycle does not change 1, that is, it sends 1 to 1 itself. We do not use this symbol and call it a 2 cycle. And in fact, by our definition of 2 cycles, the 2 symbols involved in a 2 cycle or a transposition are distinct symbols. But what if we lose this distinctness and call this type of things also 2 cycles? Then something would go wrong. What is that thing? What can possibly go wrong if that is so? If this type of notation is adopted. If we adopt this notation, then our definition of even and odd cycles will come into trouble. It will be jeopardized. That's because if we adopt the notation as indicated, then the 2 cycle, say 2, in fact any 2 cycle, any ordinary 2 cycle which we know as a 2 cycle where the symbols are distinct, can also be written as this. Why? That is because what is this permutation? What function is this? This is a function which sends the symbol 2 to 3, that is, it's the image of 2 under this function is 3, and the image of 3 under this function is 2, and the image of any other symbol, if available, is that symbol itself. Here also that is the case. The image of 2 is 3, that of 3 is 2, and that of 1 is 1. And if anything else is available, the image of that thing is itself under this function. But now you see that by the definition of evenness and hence oddness of a permutation, this permutation is odd because it's a single 2 cycle, but at the same time it is also even because it's a product of 2 transpositions. But then is an odd permutation as well as an even permutation. So that is the problem. Our definition of evenness and oddness will just simply collapse. And you can clearly see that this is not a case about just 2, 3. You take any permutation that keeps 1 fixed in your Sn, in your symmetric group Sn, whatever n may be, and you can then consider that permutation, write this extra 1, 1 alongside. Then similarly, just like this one, that original permutation, if that is even, then this will show that that is also odd. Also, if that is odd, then this way of expressing things will show that it is even also. So in general, things will come into trouble. So that's why this cannot be done. And this ends the solution and this set of exercises also, provided you deal with exercises 81 and 82 yourself. But also, of course, let me know if you do not understand the already given solution to 81, and or if you cannot solve 82. Just try and see what happens. So that's just it for this video, and the next upload is tomorrow, and tomorrow of course we are going to go back to analysis. So see you tomorrow with analysis, where we have started solving exercises based on that section where we are dealing with sums over infinite sets. So we will continue to do that until we exhaust all the stated results that are to be proved, and then we will take up the statement and the proof of Riemann's theorem on conditionally convergent series that are not absolutely convergent. So see you tomorrow with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.